Okay, so today I'm going to tell you a story about equivariance as how I see it. I might be your Phileas Fogg if you get the reference, but today I'm going to do it in 45 minutes, not 80 days, because we've got other things to do. Okay, so what is equivariance all about? Well, it's this mixing of symmetries and machine learning. Okay, so, and because we're mathematicians, computational people, right, we want to develop principled approaches for constructing neural networks. So one of the things you can do, of course, you can identify the symmetries that exist in your data. So imagine some sort of sum of three numbers, for example, right? And if I permute them all around, I'm going to get the same sum. Okay, so that would be an invariance to S3. But don't worry about invariance for a second. Just S3. Okay, so that's my group. Nice K table there. And what I want to do is create neural network architectures that take advantage of the symmetry. Okay, when performing learning. If I know about symmetry in my data, why not use it? Okay. And I suppose I need to convince you that this is actually something worthwhile doing rather than just it being some abstract thing. So here are some sort of examples of symmetries that exist, tasks that have symmetries, right? So if we start at the top left, right, I'm not a chemist, but I know for certain, right, that if you, for example, want the ground state energy of a molecule, well, it's going to be the same no matter whether I move it around or rotate it or reflect it, right? If I go to the right one, which is the n-body problem, I've got some molecules and I want to predict the sort of velocity vectors or where they're going to be at some time point later. And at the bottom left, there's a picture of a very old Netflix, I think. So, you know, imagine I have 100 friends and, you know, they've all watched some movies and, you know, they made some recommendations. They like Good Will Hunting, but they don't like, what's that one in there? Mad Men or something, right? Or Bruce Almighty, that's a very old film. Okay, you know, so if I, you know, list them, it doesn't matter which way I list them, right? It's going to be, you're going to get the same result effectively, right? Okay. And what this all really boils down to, right, is the idea of equivariance. So there's a sort of a semi-formal definition on the left-hand side. Now, of course, I've not said what the group action is, and I've not said that they're vector space and so on, right? But the way I see it, or the way I read the formula, is that if I act upon my input and I push it through, it's the same as pushing it through and acting upon it. And if you look at the right-hand side here, a simple example might be edge detection, right, in computer vision, very classic type of problem. You know, I've got a nice cat here, and I can either apply my convolution kernel and find out all the edges and then shift it to the left, or I can shift the cat and then apply the kernel, and I'm going to get the same outcome. Of course, there's also something called invariance, which is a sort of a special case of equivariance where the action on the second space, right, this W is trivial, right? And an example might be image classification. A cat over here is the same as a cat over here, right? So I would like my network to learn this without worrying where it is in space. And you may think, well, how do I actually design these networks? Well, just like with standard neural networks, right, we compose layer functions together. We have some some activation functions. And if they're all, just ignore the invariant part, if they're all equivariant, you can show that the whole thing is going to be equivariant. And then if I want an invariant model instead, I can just put an invariant layer at the end. And this is sort of analogous to convolutional neural networks. You know, if you know about those, it's pretty standard where you've got convolutional layers, right? So before I get into the actual things I want to talk about, you know, what are some of the benefits, right, of creating these models? Well, if I know something about my problem, I know some symmetries about my problem, it might be a good idea to actually bake them into the model. That's the first thing I sort of said today, right? And we're hoping that we're going to get some better performance on test data, right? And hopefully this can improve efficiency. So if you look at this right-hand side, imagine I didn't bake these symmetries into my model, let's say, right? So I want to learn something about a box, some property about a box. I have to rotate the box in all the orientations possible to even get a hope of actually learning something. But if I have the symmetry in my network, I just have to put one instance through, and the network's going to do all this work for me. So of course, and maybe this isn't clear yet, but of course, potentially fewer parameters. So we'll see later on that there's wait time that goes on in certain cases. And that means potentially it's easier to actually trade these things. Okay, so an outline of the actual talk I'm going to give. I've given these things funky names, but on the left-hand side, we've got the convolution editors, so people who've gone around editing convolutional neural networks. We have what I call the permutation pioneers. So these are people who have looked at data on sets and graphs. And then I'm going to talk about some future directions as the crystal ballers. Although where they're crystal ballers, I don't know, because they're sort of doing this work already, but we don't know where it's quite going to go. Okay, so let's start with the geometric transformations. Model. Okay, so I've talked a little bit about convolutional neural networks, I suppose, and we've sort of seen their translation equivariant. Of course, I haven't proven it to you, but you can go and look it up, right? They're not typically equivariant to problems, to symmetry such as rotations and reflections, right? If I sort of rotate this gecko, I shouldn't expect that the output is going to rotate nicely as well, right? And so the goal is to sort of generalize the CNN to exploit symmetries like this. So this is the problem I'm going to start with, right? So I've got my image, which is this gecko, and I've got one filter that's going to just go across the gecko, right? It's sort of that circular thing with the red in it, and it's going to produce me one feature map. That's just to keep it simple, right? You could have more outputs, just to give you the basic idea, okay? And I want to get this rotation, well, let's say rotation symmetry, just to keep it simple as well. So I'm focusing on Z4, right, so 4 group elements. And all I do is I take my one kernel at the top that I had before, and I just rotate it around and get 4 kernels. And then I put those kernels over the gecko, and I'm going to get 4 output feature maps, right, so 1 for each group element. And you may think to yourself, well, why is this equivariant to this group? Well, let's start off with the first case where I just put the kernels over, so that'll be applying my function. And then I do, let's just say a rotation, sort of anti-clockwise by 90 degrees. Well, that's just going to rotate all these feature maps. Okay. Now instead, let me say I rotate the gecko instead by 90. Now hopefully you can see this, but in the first case where I put this gecko over the first kernel, it's the same thing as putting the rotated gecko over the second kernel, but with the image rotated. So you're going to get the same information out, but in a sort of a cyclic shift pattern. So that's why it's equivariant, because I haven't lost any information. And this kind of explains the same thing, I guess. This is in the original paper from Cohen and Maxwelling, where you're sort of going to get it's going to move around, follow the arrows, but then rotate. So this one is going to go here, for example. And you can sort of see this. If I rotate this one, I'm going to get this one. It's just saying the same thing. Okay, so that seems promising, but there's some challenges, of course. So imagine I don't put a 90 degree or 180 or 270 or something through. I put 45 degrees through. Now what's going to happen to my performance? Do I expect my kernel to actually play nicely with my image? Probably not. And similarly, what happens if the group's infinite, right? So I've done this for one group element. That's one filter for every group element. If it's infinite, I need an infinite number of kernels under this construction. Of course, one thing I could do is discretize the thing, but then I'm losing some information. So there's some sort of trade-off potentially. And so that's why I say here it only works for what I've called small groups, right? One feature map per group element per output channel. Of course, I only did one output channel, I could have had more of them. And so we're potentially going to run into some computational problems. And finally, which is the thing that people are kind of interested in as well, is what happens if the image is not a scalar image or a feature map, but instead consists of vector fields, right? So I've got a vector coming out at every location. And if I want to rotate that, I want the vector to rotate nicely too. So then some other clever people, so that was 2016, okay, ISO 2016. Some other clever people, well, I'll get to what the clever people did. But anyway, what they did was kind of based on this idea, actually. So this is sort of from 1991, so that's the year of my birth, and that maybe makes me feel old. So imagine I give you that kernel, right? I just give it to you. Okay, some function of a radius and an angle. And don't worry about all the maths, it's just to show you the steps if you're interested. But imagine I apply rotation of some theta degrees to the kernel. Now, if you track the action and do some basic trig, what you're going to end up with is either this equation or this diagram, which is effectively saying that if I take my kernel and rotate it, I've got a linear combination of two kernels, okay, with some coefficients in terms of theta, right, in terms of my angle that I put through. Okay, so this is 91. So this is effectively people are using ideas from, pattern analysis and so on to do this. Okay, and so hold in your head basically that we've got any kernel can be expressed in any combination of these other simpler kernels. So why is this good? Go back to the GCNN, which is what the other one was called. I didn't say that. Now instead of having to take an infinite number of these kernels, I can just take these two and I get the rest of them by linearity. Okay, so I've reduced this infinite problem, which would basically be impossible, to two kernels in this particular case. Okay, so that's pretty nice. But maybe let me just go to the general case first. Okay, so I called these things filters in the other slide. That's sort of the terminology from different parts of the literature. For kernel and filter, if I use them, they mean the same thing. Okay, so imagine now I give you a finite set of kernels, right? So let's just say that, I didn't actually write this, let's just say there are n of them, okay? Then we call this thing a steerable basis if first of all we can write the kernel as a linear combination of them, and secondly, if I act upon it with my group element, what I get out is a linear combination of the kernels with some coefficients that depend on the group element. Okay, so I'm still getting this linearity property. And ultimately all I need to do then is convolve with those n kernels, right, to get any particular one. But of course, where do I get them from, right? I've just said, suppose we have them, okay? And the answer is really, well, there's many different ways of doing this, but the one that I quite like is taking irreducible representations of the group. Okay, so okay, so this is probably one of the more messy slides, so stay with me. Right, so, recall, so SO3, there are these irreps, okay, irreducible representations. Each vector space has a dimension 2L plus 1. And each vector space has a basis of functions called spherical harmonics of degree L. Okay, so of course they're going to be 2L plus 1 of them, and they go from this order of minus to plus. I think I've got the numbers in the wrong, I've done this incredibly, anyway, it doesn't matter. Okay, so then, in theory, right, we can define a general steerable kernel, right, as just being a linear combination of all of these spherical harmonics across all degrees, right, or equivalent to say the kernel lives in this infinite direct sum of these irreps. Okay. Now, I might lose you here, but anyway, let's go for it. What I claim is that this thing is actually a steerable basis. Now, don't worry about the formula. I'm going to show you where this comes from. Okay. But effectively, you can show that if you act on this thing, here's your, in this bracket, here's your constant back, right, depending on the group element. Okay, so it is steerable. I'll show you why in a second, where it really comes from. But in reality, what happens is that we truncate, so you see it's infinite, we truncate this thing. Because each irrep is sort of corresponding to some geometric property, and we only care about certain degrees of these irreps, right? We're not going to go all the way out, we're just going to take a finite set of them. And so ultimately, once again, we're back in the same world. We only need to perform a finite number of these convolutions. And as I said at the bottom, it looks scary, but it's part of a general phenomenon. Okay, so let me show you why it's part of a general phenomenon. Here's that equation again. And instead of the infinity, I put L equals 1 as the max at the top. Okay, so that's just, I've just taken that for simplicity, but it would work if you took a higher number for the max. Then what I can do is I can write my kernel as a vector, right, with all these spherical harmonics of the different degrees and orders. And I've suppressed the function arguments to keep it simple, right? Then what you can show is that what's happening up here is just this big matrix multiplication. But interestingly, it's a block diagonal matrix multiplication. Okay, And if you know a bit about group representation theory, what's really happening, and maybe I'm jumping ahead, but what's really happening is that each irrep as a representation is acting upon its individual vector space, right, in a sort of this block diagonal fashion. And that's because the kernel lives in a direct sum of these irrep spaces, right? So that's basically what I say here, right? So we construct our kernel to live in this particular direct sum space. Each vector space, the VL, is acted upon by DL, right? Under some group elements. And the steerability condition is just saying, let this big representation, which is a direct sum of the individual representations, act on my kernel. Okay, so I'm going to get that steerability automatically. Because if I take the spherical harmonic basis, I'm going to get the block diagonal matrix. Now, you may have thought of this already, but my kernel is now on a Fourier basis, right? So I've changed space as well to do this. And this is kind of where I've left it, so I didn't want to get too into the depth of it, but I'll explain something in a second, okay, about the activations. So this is, what I'm trying to explain really is that this is a general phenomenon. So if I take a compact group, I can use some what I call heavy machinery, this Peter-Weil theorem, to get the irreps of the group and do this direct sum block diagonal matrix representation effectively. And also one thing we can do, of course, is not just take one irreducible for each, like we did to a direct sum of one irreducible of each for each L, or I can take multiple copies of a particular one. I don't have to take one of each one. Okay. And I did spherical harmonics for you, but you could do this, you know, SO2, for example, with circular harmonics. So it would all work out, except the irreps would be one-dimensional. So I chose this one because you actually see that nice block structure rather than just a diagonal matrix. Now, because I want to get onto some other things that I personally find more interesting. Here's a list of literature where, you know, I've basically shown you these top two with maybe a little bit of the third one, right, where Cohen and Venning really came up with a lot of this, let's say, infrastructure, right? And it was then built upon in individual cases. Then there were particular ones for looking at data on the sphere. Then I say here this customizable equivariance for the tensor field networks, this idea of taking individual geometric tensors and mapping them to irreps, right? So you actually just directly picking that direct sum based off your data, what particular properties you're wanting to model, right? I said something about the activation function. So because I'm now on this Fourier basis, like if you want to apply ReLU typically, you want to do that, you don't want to do it on a Fourier basis, it doesn't work very nicely. So typically what you have to do is you have to map back to spatial, so you have to take an inverse Fourier transform, apply your ReLU, and then map back to Fourier world and then keep going. So you're having to do these constant mapping back and forth, which is obviously costly. What Condor and other collaborators, including Shubhendu Trivedi and so on, came up with was this Kedge-Gordon nets. So what they did was they stayed in Fourier world and they started taking tensor products of these irreducibles. And what you can do is you can write them as a direct sum again of the irreducibles. And that's a non-linear operation. So you just, and you can find the coefficients, right, for the particular group, typically. Well, for SO3 you certainly can. So that was a way out of trying to do this back and forth activation function business. And then, yeah, there are many more. I mean, I know this is being recorded, so I won't say too much, but I even reviewed a paper that is a derivative of this one, so 2016, you know, last week for ISOML. So it's still being worked on, this area. I mean, I personally don't. I work on the second part more, but yeah, it's still a hot area, even though it's, you know, it's been around for 10 years. Okay, so I'm going to move on to something I personally feel more comfortable with explaining, but anyway, there we go. So permutations on sets and graphs. And so basically the way the papers work, as I showed you before, it sort of started in 2016, those papers, and went forward. Here we've got like this parallel world of 2017, 2018, 2019, doing something different, right? So instead of these rotations, or translations, or even convolution, we're now just looking at set data. Okay, I've showed you some examples right at the start, but point clouds might be another one. And just to keep it simple, what you do is you index the standard basis of Rn, right? Each index will be an element of your set. And your goal, of course, is to design equivariant layers, right? Linear layers to permutations. And what these guys did, so this was really the first paper, the sort of the seminal paper, I would say. It showed that if you have an invariant function, that's linear permutation invariant, right? It's going to only have one parameter. And if it's equivariant for n greater than equals to 2, but that's basically every case, it's going to have two parameters. Now, if you think about an n by n matrix instead that didn't have any equivariance on it, it would of course have n squared parameters, right? So we've got a large reduction by including this symmetry, right? So basically what we're saying is if I know my symmetry is, the symmetric group Sn, or S5 in this case, this is going to be my equivariant wave matrix in the standard basis, where you're going to have one parameter down the side, that's the yellow, and all the blue ones are the second parameter, okay? And of course, this just goes all the way out, as I explained over there. Here's another paper that's Syamak Rambakash. He was also an author on the deep sets paper. So these papers came out pretty similar time. I think the first one was ICML, this one's, oh no, the other one was Nurex, this one's ICML. But I think the first one came out first, actually, the other one I just showed you. So they developed a way of creating equivariance for set data, but the sets are different sizes now, right? So you've got a size n set and a size m set. And they did a number of things, but one of the things they particularly did was trying to work out equivariance for an automorphism group of the graph, where the graph had, let's say it's going to have n nodes at the bottom and m nodes at the top, right? So here you've got 3 and 6, right? Which is going to correspond to your wave matrix of 6 by 3. And effectively, what they did was they showed that if you could draw lines between nodes, and firstly, each line sort of between numbered nodes corresponds to a weight. Right, so I don't want to cry across the whole screen, but you see, for example, the 1 with the orange corresponds to 6, that's down here, right, this way. And they also showed that then, so long as you maintain the structure of this this pattern, right? So they've got an action going across the top and a reverse one going across the bottom that maintains the pattern. You're going to get the same structure, basically, right? So you're going to get this automorphism group equivariance coming out. So this is important because effectively what they're saying is, if I know my permutation set effectively or group, then I know what my wave matrix is going to be, and vice versa, effectively, right? This was developed even further. Okay, so I would say, I know I said the other one was similar. I think this is the most important paper probably in the whole area, by Haggai Maron and his collaborators in 2019, where instead of now looking at sets, right, they looked at higher order tensors. So for example, if you're just say Rn tensor k, if your k was 2, for example, you're going to get graph data, adjacency matrices and so on, right? And they found a whole basis for these maps, right, where there's some conditions on NL and K, but what they showed was that the basis is related to the Bell numbers. And if you know about Bell numbers, they're related to set partitions. I'm going to show you that in a second. I won't jump the gun. But you start getting these very nice patterns, right, with these wave matrices, but each color is going to correspond to a particular parameter or weight, right? I don't know what size it's for, but it's obviously very big. Yeah, so something nice diagrams like this, right? Okay, so I could show you their proof. It would be probably too much for a lecture like this. So it's a bit naughty. I'm going to show you my proof, which I did for a paper a couple of years ago that got in last year, which hopefully is a bit more intuitive than theirs. If they're on the call, sorry, Haggai. Right, hopefully he's not, or doesn't see this. Okay, because he was my PhD examiner, so yeah. Don't be rude. Okay, so no, it's a very, very good paper. I would not have got this result without him. So yeah. Okay, so what am I going to show you? So we want this basis of these SN equivariant maps, right? And we're going to do the standard basis of Rn. So every Rn, copy of Rn, has a standard basis. And the way the proof, I'm not going to show you the full proof, I'm going to show you sort of the intuition by the proof here, is that I'm going to go down this diagonal where I'm going to correspond this basis of matrices effectively to orbits of the action of Sn on basically the set of L plus K length tuples, and each element can be an element from 1 to n, right? So for example, you could have an L plus K length tuple with all n's in it if you want, or all ones, or various different choices, right? And then what I'm going to show you by example is that each orbit corresponds to a set partition. So a set partition, and this means of 1 to L plus K, just means split your set of 1 to L plus K up into a disjoint union of subsets. And we're going to call each subset block, it's just terminology. So, and each set partition can be given in the form of this nice diagram, where we're going to have K nodes at the bottom and L nodes at the top. So K is 2, L is 3. And this particular diagram is corresponding to the set partition where there are 2 blocks, one containing 1, 4, and one containing 2, 3, and 5. Okay, so I'm going to go down this right-hand side. Right? Now, this again looks maybe complicated, but I'll explain it. So, if you have a linear map from a K-order tensor power space of Rn to an L-order tensor power space of Rn, you can just write it as a linear combination of matrix units, right? So this Eij just means 1 in the Ij position and 0 everywhere else, right? So they've got 1, 1 in it. And if you literally follow the definition of equivariance I showed you, right at the start, just follow the maths, it's like 4 lines, you're going to get this equality, where you're just getting a relationship between the coefficients. And so what you can do is you can just lift this to an action on the set, right? Just literally directly off the indices. And so that shows the basis of matrix units corresponds to these orbits, okay? Now I'm going to go across the bottom between orbits and set partitions with an example. So I picked some random numbers just to keep it nice, hopefully, so relatively small numbers to keep it nice. So I've got S3, and I've got L equals 2 and K equals 4. So I'm going from 4 tensor powers to 2 tensor powers, and I'm picking some orbit. So to pick an orbit, I can just pick any old random element, right? So I pick this random element, 2, 1, 1, 3, 3, 2. And what I want to show is that it corresponds to a set partition diagram, okay? So how do I do that? Well, I put my K, which is 4 nodes across the bottom, my L node, which are 2 across the top. I take my Ij and just label from the top to the bottom, right? And then I connect nodes up, if and only if they have the same label, right? So the ones that are connected, for example, right? So I get a set, if I delete these numbers out, I now have a set partition diagram, right? Which I can rewrite set partition if I wanted to, but I'll keep the diagram because that's how I view it. Okay, but of course I've got to show this diagram that I get is independent of the choice of class representative for the orbit. So if I give you another one, so I've done some action, I don't know which one I've done, 1 to 2, 2 to 3, and 3 to 1, and I do the same procedure, I'm going to get the same diagram. So hopefully that may convince you that that's enough, right, just for now. The other way, of course, I've got to do is I've got to take my diagram, any old random diagram that has n blocks, and get out an orbit. Well, the way to do that is just label the blocks, because they're in blocks, 1 to n, in any order. Push them to the edge, like I've done here, right? So I can label this as 1, if I took this one, label this as 1, this is 2, this is 3, push them out, and I'm going to get my orbit out because I can act upon each of the nodes again. So ultimately, by combining the sort of triangle I showed you, basis matrices correspond to set partition diagrams having at most n blocks or subsets. Right. So the last bit I'm going to show you, of course, is how to actually get a wave matrix out. Slightly different example, just again to keep it all on one slide, or a couple of slides. Here I've got S2 now, so that's n equals 2. I've got a 2-order tensor power space, and I'm going to a 1-order tensor power space. Right? So the first thing I need to do is find all the set partition diagrams, so 2, 1, that have at most 2 blocks. So there are 4 of them. You know, that one has 1 block, and these ones have 2 blocks. And notice I don't have the one that has 3 just dots without anything, because that would have 3 blocks. Right? It's too many. And if I take, I'll do it for each of them, I'll just take this as the example. If I take the second one as my example, what I need to do is label the diagram with, or label the blocks of the diagram with the numbers from 1 to n, right, or 1 to 2, and then push them out, right? So I've labeled it 1 and 2, and I've labeled it 1 and 2 this way, and then I've pushed them out to the edge. I can just read off the ij values immediately from the diagram, convert them into matrix units, and then add them. And if I do this for each one, I'm going to get a diagram corresponding to a matrix, a basis matrix. I weight each of them and add them, and I get this as my weight matrix. Right? So I'm literally saying if I have an S2 equivariant map from this space to this one, that's the weight matrix I'm going to use in my neural network. Okay, and it's got that guarantee of that property, right? The S2 equivariance. And you can do this for different choices, right? NKNL. Okay. I would go on, but I'm giving away my upcoming talk, so I don't want to do that. You can do other groups. Okay, so if you like that, you're going to like my upcoming talk. If you didn't like that, well, come anyway. I'm sure that'll be something you like. Okay. So just another bit of literature, since this is meant to be an introduction, right? Is those 3 papers I showed you, probably the 3. I don't want to discredit the other authors. They're probably the 3 most important ones. This last one's also quite important, to be fair. But there's a paper looking at interactions between different sets now. So it's got this direct product of symmetric groups going on. Second paper probably received less attention, maybe than it should deserve. They looked at general vector spaces and just said, well, if I can decompose each of them, I can apply Schur's lemma and get the weights. That's quite nice, but then you've got computational problems, so maybe that's probably why it hasn't received the attention it deserves. This third paper looked at organising the basis that Haggai Merrill and his collaborators found to try and improve the computations. And this last one also did a bit of S and equivariance for other groups in a different way. Instead of doing it analytically, they came up with effectively this computational inverse computational problem and acted out of particular equations. Also quite a nice paper. Okay, so we're nearing the end. Stay with me. We're at the exciting bit, which is the crystal ballers for the future directions. We're almost there. Before I get there, I imagine there's some graph people online who are going to come and shoot me. I haven't talked about equivariance on graphs. Hey, it's my talk. I can do what I like. So some interesting work. Taking equivariance and trying to change attention to make equivariant to SE3, so that was Fabian Fuchs and collaborators. Equivariance and graphs is important, to be fair, it is important. Just didn't fit with the convolution necessarily. So this particular one by Sartoris, so there's EGNN, where it's looking at, say, molecular data, and you wanted to maintain the rotation and translation symmetry. A lot of these coming from message parser, which is the Gilmer paper. There's questions about universality and expressivity. So, you know, if you know about the universal approximation theorems of the 1990s, it's a very similar type of question, and it's been answered for certain of these architectures I've shown you, and some open questions, obviously. Then there's what I would call the Dutch school of equivariance, David Roux in particular. A whole host of papers looking at equivariance for pseudo-orthogonal groups by considering Clifford algebras. They've had a host of Isomel and Europe's papers, printing them like it's going out of fashion. And equivariance in reinforcement learning. You know, if I want an equivariance policy or something like this. Also quite interesting. Yeah, so if you're interested, I recommend you go and check them out. But actually, let's okay, right, I don't know where this is going to work, but this could be interesting. Okay, so some interesting future directions. I was going to start there, but I put a picture of Brad Pitt on the screen. So I think I have to start there, don't I, really? Right, why have I put Brad Pitt on the screen? Probably the only Equivariant talk that will have him, I hope. So what's the idea, right, we've been doing? We believe that like the data that we have has these perfect symmetries, okay? Now, Brad Pitt's a bad example. He does have quite a relatively symmetric face, but this particular image from Google Images gave me one that's sort of not quite, you know, sort of eyes a bit of a slant and his, you know, his smile's a bit of a slant, right? So the question is, well, if we relax this equivariant constraint, right, maybe we're going to get some better models out, okay? Again, a whole host of papers that are attacking this problem, all very current. There's this issue about scaling equivariant models. Okay, so maybe this is a nice thing in practice, you know, in principle, but in practice, can we get the requisite scale on these things? That paper there's from October 24, and they've shown some nice results relating to equivariant transformers versus just standard transformers, and showing in their belief that these things can scale, but then there needs to be a lot more work on this. Right, goodbye, Brad Pitt. Two very different things here now. So, equivariance and weight spaces. So maybe you know, maybe you don't know what weight space is. So this is my understanding. I'm sure someone will tell me otherwise. Right. So basically, what you do is you've got your input image. So like it's 5, and it's the same output. And what you do is you train a bunch of models to learn that the input from 5 is 5. And then what you do is you create this new deep weight space architecture that you hope is going to learn from the neural networks themselves that this thing is 5, right? And you can potentially do this in an equivariant way by taking advantage of the symmetry in the actual neurons, right, in the networks. So this Navon paper in particular, probably the most important in the area so far, but it's being worked on, especially in Israel. I think a lot of Haggai, Maril's team and so on are working on this. Equivariance canonicalization, this is also very new. Saw a few of these posters at ISML last year. So what's the idea? It's sort of the inverse of GCNN. So with GCNN, what we were doing was basically creating a new feature map or a new kernel for every single group transformation, right? This is kind of the inverse, because what you do is you basically split the equivariant and the invariants out of your network and create this new network called a canonicalizer that you train. And so here I'm putting this upside down. I say I borrow this. I'm putting this upside down cat in, and I want this network to learn the correct orientation for the image. Okay, so if I put it in at 45 degrees upside down, I still want it to learn this. And then I just put this through any old network I like and hope it learns cat. So I split the equivariance directly out of my network. Now, this looks amazing in theory, and they've had some good results, but you know, one potential problem might be, for example, is joining these two networks up. Let's say this network here learned on cat images that were upside down, just for sake of argument, right? If I put that network with this network, it's going to do badly, okay? So I want the network here to match well with the network I'm doing over here. It's not just an immediate fix, right? Certainly a lot of papers, or some papers now coming out on this. Three more. Okay, so stochastic equivariance. There's a couple, probably this one by Rob Cornish at Oxford, is very current, you know, literally late last year, where instead of doing this exact equivariance that we've seen before, each input models to a probability distribution y, and you're effectively trying to model equivariance through what they call Markov kernels. So for example, you've got this image of a banana, and you're trying to roughly work out where it should be, right, in some sort of distribution. This one, the equivariance and category, this is one I'm probably most excited about personally. It's something I'm going to be working on hard. Don't tell the world that. But effectively, we're going to take this very well-known, very highly researched stuff from the 1950s, 1960s, category theory, and try and implement it on equivariance. And there was some, particularly this last one, ISML last year, that did this and came up with a bunch of interesting models. Yeah, get nice diagrams like that as well at the top. And then the very final thing, which will probably make you wonder why you sat here for 45 minutes. I've got 45 minutes if I did it in time. No equivariance at all. Maybe it was a complete waste of time, this whole talk. Some people have got some very nice results, recent results. Particularly this image is an image of a protein. Don't ask me which one, I don't know. Just by shoving loads of computers in still, can we get some great results? Well, they show we can by predicting properties of molecules. These guys from DeepMind, I think, at the bottom here on the right. And yeah, for the people online, if you're not part of the Hubble, part of Imperial, that's my contact if you want to get in touch. But yeah, thank you very much.